So let's say I'm dealing with some function called f of x, and let's say that it's a continuous function that is smoothly varying. Since I'm normally concerned with physics problems, that's normally the case in physics. And let's say that this function is something sort of nasty that I don't really want to deal with mathematically, so I want to sort of cheat a little bit and make an approximation. So how do I do that? Well, the easiest thing I can do is to just pick a value and say that f of x equals that value. And so say I'm doing an experiment and I know that my values of x that I'm going to get are pretty close to a. So if I just say that f of x is equal to this value f of a, that since my x doesn't vary all that much, that this should get me pretty close to the right answer, and then I'll just have a constant term to do my math with, and it'll be very easy for me. So this first approximation is this approximation. I'm using my eraser. F of x is approximately equal to f of a, right? I know that my x values are pretty close to a, and it doesn't vary that much over the interval around a. So this should work pretty well for me, and we'll call this the zeroth order approximation. Zeroth order, and I'm naming it the zeroth order approximation because it depends on x to the 0, right? It's just constant. X to the 0 is 1, and that's a constant. So maybe this worked all right for me, but maybe I want to be a little more precise. I've gotten some results that weren't all that good, and I'm blaming it on my simple treatment of this f of x function. So I want to do something a little bit more sophisticated, still pretty simple. Instead of doing a zeroth order approximation, I'll do a first order approximation and approximate that this function is just a line. It's not quite constant. It does vary, but I'll assume it's a line, and that'll still give me something pretty simple, but it'll be a little better than just assuming it's a constant value. So now instead of saying that my values of x are going to be so close to a that I can just pick a constant, I'll pick another point and say that my values of x are somewhere between a and this other point b. Now if I make an approximation to a line here, I have to find out what slope to give this function in this interval where I care about it. So here we have f of a and f of b, and there's some slope in between f of a and f of b. That slope is f of b minus f of a over b minus a, right? So if I'm approximating this as a line, if this is pretty much a line, that's taking the average slope of something that's pretty much a line is really the best slope I can give to my approximation. And I'll draw it a little bigger here, zoomed in to the interval a over b, or from a to b. And so this is my average slope right here. And just to write this in a more compact way, we'll use the mean value theorem, which I won't state formally, but all it really is that if I have a function going from point A to point B, I can take the average slope here, and there has to be some point along the function that has the same slope, that the derivative is the same as the mean value of the derivative. So this is the mean value theorem, just in a nutshell. And I'm going to call this point, just to pick something to call it, I'm going to call it epsilon. And it's not really going to matter that I've picked epsilon. Epsilon is not going to appear in the final product of this video. So it's just something, just a way to write it. So this average slope is equal to the slope, the derivative of this function evaluated at the point epsilon. So I'm going to solve this for f of b. So I'll get f of b equals f of a plus f prime evaluated at epsilon times, I'll shift over a little bit, b minus a. b minus a. And now, does it really matter what point b I picked? As long as it's somewhere close in here, as long as it's within my, as long as my approximation is valid that this is a line, then the point I picked for b didn't really matter, and I can just say, I can just label b as just any value of x. And obviously this isn't a line, so the point I picked does make a difference, but as much as I care about how accurate my approximation is, as long as it'll be close enough, I could have picked any x and I would have gotten something pretty close, assuming my approximation is accurate. So within our approximation, we can say that b, we can just change b back into x. Right? So I'm going to write this, I'm just going to change b into x, since if our approximation is correct anyway, this will be close enough. Right? So now I have another approximation for f of x that depends on x to the first power. Right here, x to the first power. So this is a first order approximation. First order. So first order approximation. All we've done is we've taken the slope between a and some point nearby, and we've approximated our function as the value at a, and then plus the average derivative in the region as a or multiplied by the difference between x and a. So it's basically just following this dotted green line. That's how we've approximated our function. So say I use this and it gets me a little bit better results than my zeroth order approximation, but let's just say that it still isn't very good. I still am not quite satisfied with how accurate this approximation is. So I want to go one step further. So I want to make a second order approximation that depends on the square of x. It's a little more sophisticated, and hopefully this will make it good enough for me. So to make the first order approximation, to get here, I used the mean value theorem, and we said that the slope, the average slope, occurs at somewhere along this line, or somewhere along this function. I should try saying that again because it didn't go that well that time. If I have a function that goes from point A to point B, there will be some point along that line that has the same slope as the average slope. And I used that here and wrote this down. Well, we can say the same thing. So say I take the derivative of this whole function, f of x, I take the derivative of this function and I plot that. So I plot f prime of x. I can make this same exact argument, saying that say that instead of f of x, this was, or f of a, this was f prime of a. So this is, it would look different, but for the sake of argument, I can plot my function f prime, and I can do the same thing. I can go from f prime of a to f prime of b. So instead of finding the average first derivative, I'm finding the average second derivative of this function. Still using the mean value theorem, but using it on the plot of the first derivative instead of the function itself. And so I can rewrite this equation, except instead of finding the average value of the first derivative, I find the average value of the second derivative. And so I can write f prime of x equals f prime prime of A plus f double prime of epsilon, and this isn't the same epsilon. I'll write epsilon 2 just to clarify that the average first derivative doesn't necessarily occur at the same point as the average second derivative. So f double prime evaluated at some point in there times x minus a. See, now I have an approximate form for f prime of x, and this should have been a squiggly equals, since I'm making an approximation. This isn't the real shape of the function, but this is my approximation, and this is also a squiggly equals, saying that this is an approximation. But now if I want to get from my approximation for f prime of x, I need to integrate this function. So let's integrate this. So I'll do the indefinite integral, since I'm just trying to get this still as a function. I'm not plugging in values of f prime of x, and my differential is going to be x minus a, just to make it work out pretty. X minus a equals f prime of a times x minus a, and then the next term is plus f double prime of epsilon, since epsilon 2, since this is a constant function, it's just evaluated epsilon already, so the integral doesn't affect this, and then we'll integrate x minus a squared dx minus a, or x minus a dx minus a. So really I've just made a u substitution, but written it inside here. So now we have to multiply this term by x minus a squared. And then, since this is an indefinite integral, I need to add a constant of integration. And if I look ahead, and I know how to evaluate this constant, because if I plug in a, this has to equal f of a that I have all the way up here. I know what f of a is, and if I plug in a for x, a minus a, this term goes away. A minus a squared, this term goes away, and so I have to be left with f of a. F of a is my constant of integration. And so I'll come back down here, and I'll rewrite this in a simpler form. I'll use yellow. So the integral of f prime of x is f of x. And since we've made this approximation that it only depends on x squared, we have a squiggly equals, so it's approximately equal to f of a, which is our constant of integration, plus this term here, which is f prime of a times x minus a, plus this next term, which I've just realized I've forgotten a factor of 2 in this term. Since I take the integral of x, or x minus a, u is x minus a here, so I've taken the integral, it's x minus a squared over 2. So excuse me, I missed that the first time. Hopefully it didn't throw you off too much. But anyway, add this term, f double prime of epsilon 2 x minus a squared over 2. That's a terrible line there. Over 2. And I haven't written it very compactly, but we can see that this is a second order approximation. So we have a term that varies with x squared. So this should be a little bit better. so this is a second order approximation. Second order. Or quadratic. A quadratic approximation is as it's sometimes called. So now say that my experiment is really finicky and I'm still not satisfied with my second order approximation. I'll quickly do a third order approximation, and then we'll start to see a pattern. So if I still use this mean value theorem, and I write down what we got from it here, our first order approximation, and I'll just, instead of adding 1 prime to each term as I did to make the second order approximation, I'll add 2 primes to each term. So we'll end up with, let's see, I'll change to blue. So we'll get f double prime of x is approximately equal f double prime of a plus f triple prime, there are 3 primes here, of epsilon 3, so this is just one other point, since the third derivative, the average third derivative doesn't occur necessarily at the same point as the second or first derivatives. So just at some point, doesn't matter what it is, but just labeling it differently to emphasize that it is not the same as this other one necessarily. But anyway, this plus or times x minus a. Now we can integrate this just like we did before and get an expression for f prime, right? So just quickly I'll write what we get from f prime. F prime of x from our requirement for using the mean value theorem for the third derivative, we get f prime of x equals f double prime of a times x minus a plus f triple prime of epsilon 3, which again is just some point. You don't really care what it is, times x minus a squared, and then our constant of integration in this case will be, and I've forgotten my factor of 2 again, so over 2, and then our constant of integration this time will be f prime of a, for the same reason as before. And I'm going through this quickly, and you should check the steps along the way in more detail, but it's the same process as we went through before. So now we have an expression for f prime, and now we need to integrate again because we started with the third derivative. We need to integrate once more, and we'll get our third order approximation. Our third order approximation is f of x is approximately equal to f of a plus f prime of a, and this is our constant of integration in this final integration we do, f prime of a times x minus a plus f double prime of a times x minus a squared over 2. So we get this factor of 2 from the integration here. We take this to x minus a squared, and we'd have to divide by 2. And then our last term, scrolled way up. And our last term here is plus f triple prime of epsilon 3, some point, times x minus a cubed over 2 times 3. So we have this factor of 2 here coming from our first integration, and then our factor of 3 coming from the second integration. And now we can spot a pattern. We can say that each time we go to a higher order, we end up with the function evaluated at a plus some other term evaluating the derivative with the highest order that we're approximating to. So if we go down here, we see that instead of having to plug in some value here, we actually ended up with the derivative at our value a, and the next term had this some point we had to plug in, and then the same thing for the third one. Each time we get one further, and we get the same form of our approximation, except we get one further in f of a. So say we did this an infinite number of times. Say we got tired of taking one approximation at a time and trying it out. Say we just wanted to do this for an arbitrarily large amount of time. We can notice a pattern, and I'm just going to write it down since this video is getting a bit long, but you can go back and see the patterns as they're unfolding. So each time we do this, we get closer and closer to the real way this function acts around the point A. And if we do an infinite number of these, you can see that this term is getting smaller and smaller since the denominator is a factorial actually. So eventually, if we do infinity of these, we won't even have to pay attention to the last value. It'll be insignificant. So we get what's called the Taylor expansion, or a Taylor series expansion of a function. Taylor series expansion. Taylor series. And that is the function f of x equals the sum, so we're adding up each of these terms, the sum from n equals 0 to infinity. So we're doing an arbitrarily large number of these approximations, equals the function, the nth derivative of the function. So I've taken n derivatives of the function, so taken 0 derivatives, taken 1 derivative, taken 2 derivatives, 3 derivatives. So as far as I want to go, take n derivatives of the function of x, and then I'm going to multiply by x minus a to the n. So here we see that x minus a to the 0 is in this term, so n equals 0. The first term has no x minus a's in it. The next term has x minus a to the first, and so on. They each have an increasing x minus a power. And then divided by n factorial. And so we see that the first term, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and we can see that this is 3 factorial. This is 3 times 2 times 1. So in keeping with this pattern, and you can tell that say we took the fourth derivative, we would have to integrate 3 times, and we'd end up with a fourth root, or not a fourth root, but a fourth power term, and a 4 factorial on the bottom. So this here, oops, I've shown you my cheat sheet. I wrote it down ahead of time just to make sure I didn't screw it up, and so you've seen it twice. But anyway, this is the Taylor series expansion of a function, and we've gotten there by taking things one by one, and I guess it's a proof by induction. So hopefully this helps you understand what's going on when we say that we're taking a Taylor series of a function and when it's useful. And normally we don't need all infinite terms of a function. We just keep the first few, or as close as we need to get close to the correct answer of the problem, or something that agrees with experiment, or if we needed all infinity terms, we would just probably use just use the function by itself. But anyway, Taylor series is a very, very useful thing in physics and in other areas that include math. So here it is, and I apologize for how long this video is. We're creeping up on 25 minutes, and but hopefully it was useful.